we do with impulse before we do a little activity tomorrow and then move on with conservation of momentum on Monday. We're going to talk about impulse graphs here today. And when I say impulse graphs, really what I mean by that is a force versus time graph. Force versus time, force on the y-axis, time on the x-axis. Whenever you see a force versus time graph, I always want you to think 3 words. Always. Just like I said, when you see a funny angle, I always want you to think 5 words. I don't like funny angles. When you see a force versus time graph, I always want you to think 3 words. Area equals impulse. Every single time. Area equals impulse. Whether or not calculating the area of the graph gets you the answer you're looking for, it is going to be step 1 in getting you the answer you're looking for every single time. Sometimes the only step, sometimes step 1. But it's always going to be the first thing you're going to think of. Now, if we are looking for impulse, we're going to calculate the area, and that's easy, right? If it's a rectangle, it's base times height. If it's a triangle, it's 1/2 base times height. If it's a kind of a combination of rectangles and triangles like this, then we got to break it up into sections, but we can do that. Remember those V versus T graphs last year in Physics 20? We had to find the area, same thing, right? The area above the x-axis is a positive impulse. The area below the x-axis is a negative impulse. So this would be a positive area right here, or a positive impulse, a gain in momentum. This would be a negative impulse down here, a loss of momentum in the positive direction. To find the total impulse, or the total change in momentum, we'd simply calculate both of those, add them up, being sure to account for the negative if there is something below the x-axis. Now, if you're simply asked to find the impulse, like we were, by the way, a week ago on the Physics 30 diploma exam, got a graph like this, find the impulse. It was almost a gimme. Like it was almost a gimme question. Then you stop, you're done. You might be asked to solve for something else, though, not the impulse. I don't care. This is the first thing you're going to do anyways. Okay, area equals impulse. But if you're asked to solve for something else, like the mass or the change in velocity of the object, then we're going to have to do something, another step, step 2, we'll call it. We've already found the area. The area is equal to the impulse. And the impulse is equal to m times delta v, mass times change in velocity. So you've got the area, 1/2 base times height, or whatever it is, equals the impulse. Set that equal to m times delta v and solve for the variable you're looking for. Now I got a big bolded sentence over here, do not use. Do not ever use this. Don't use F times delta T. Technically it's valid, but the force that you're looking for is an average force. Like, what's the average force here? Look at this. The force is changing. It's changing nonstop here. What is the average force? I don't know what the average force is. Without knowing what that average force is, you can't use that equation. Don't even try. Get the area equals the impulse, and then if necessary, set it equal to m times delta v. Now, before we do an example, I will caution you on one more thing here. We always think area equals impulse, but we always, for this graph or any other graph for that matter, we should always check the units. Are they standard units? Newtons and seconds in this case. The one thing that could have led to a mistake a week ago on our diploma exam was that the x-axis for time was in milliseconds, not seconds. People should have recognized that. People should have caught that. Most people probably did, but a few people probably didn't. If it's in milliseconds, that's okay. You just have to account for that when you're finding the area, right? Milliseconds is 10 to the minus 3. Just add 10 to the minus 3 on at the end of everything when you're calculating that area. It's not hard. You just got to remember to do it. Let's take a look at our last example of the day here. 45 kilogram truck, 4,500 kilogram truck begins at rest and accelerates over time as illustrated by the graph. What's the impulse experienced by the truck, and what's the final speed of the truck? Graph's a little small up on the board, but I think you can see it probably a little bit better on your page.
Yeah.
Yes? This is a force versus time graph. What three words come to your mind right away when you see this graph? Yeah?
Area equals.
Yes. Area equals impulse. Every single time, right away. Area is equal to impulse. Now, this is a little bit trickier because we've got like all kinds of different sections of this. We've got a triangle right here and a rectangle right here and a triangle right here. And then we got another triangle over here. The area of the first triangle is 1/2 base times height. The base is 5 seconds, and the height is, oh, look at this, force times 1,000 newtons. The height isn't 15. The height is 15,000. We've got to watch for those units. 1/2 of 5 times 15,000 is 37,500. The second one's a rectangle. It's easier. The base is from 5 to 15. The base is 10. The height is 15,000. Third one, it's a triangle again. The base goes from 15 to 20. It's 5. The height is 15,000. And the fourth one, why am I doing that in a different color? Yeah, you don't have to do it in a different color. I'm just doing it to draw attention to the fact that there's something different about it. Area 4 is 1/2. The base is 5 again. What's the height? We're going from 0 down to 15 down here, 1,000. But we're going to make it negative 15,000 because it's below the x-axis.
Do you have an extra 0 in your area?
No, 150,000 is right.
Oh, it's 100.
Yeah. We add these up. 37,500, 150, 37,500, negative 37,500. We end up getting 187,500. So the impulse is 1.88 times 10 to the 5. If you want to find the force, the final speed of the truck, we're going to say delta V is equal to impulse over the mass. But we just found the impulse, right? It's 187,500. And the mass is 4,500. It gives me 41.7. Now, technically, know that I've just found the change in velocity, not the final. But what was the initial? 0. Okay, so if the initial is 0 and the change is 41.7, then what's the final going to be? 41.7. So I've just found the final velocity, right? Notice what I did not use here. What didn't I use? Force times time. Partly because it just wouldn't have been helpful, partly because it would have been just wrong to use. I never use that. One question for homework tonight. It should go really quickly for you. You might even, probably not finishing class actually, but worksheet number 2. Continue on the worksheet you were working on. Question number 9. Worksheet number 2, question number 9.